All right. Hello, everybody. Welcome back to Lebesgue measure via Riesz Representation Theorem from Walter Rudin's Real and Complex Analysis classic math book. And this is part three. So, what I want to do today is I want to say a few words about vector spaces, and I want to state the theorem. And then I want to explain how it constructs Lebesgue measure. Um, and then I want to start the proof and see how far I get before it feels like the video's too long. I know this is like probably the worst possible format for YouTube. That's why we're here at Anti-Algorithm Math, okay? We give you the math that no one wants to see, but it's actually super cool. And, even if you kids want to watch like, something with a lot of cuts, or like a lot of fancy pictures, or I don't know what, dancing or adorable goats. I mean, nothing against all that stuff, but there's other things in life besides something that's constantly giving you extensive stimulation. Sometimes you need to like focus and think about things, and there's a lot in human life that requires deep thought and not just constant search for entertainment and stimulation. Okay, sorry, I don't mean to get so philosophical on you. Let's roll in here. So, so Rudin defines a complex vector space. Um, so uh, I'll tell you where this ends up making a difference. So R will stand for the real numbers, C will stand for the complex numbers, and at a certain point, it'll come into play. We don't really need, in my humble opinion, we don't really need a complex vector space here. Um, it's not critical to the proof. Um, Pretty much what we do in the proof. What works over the real numbers. Um, so there's really no particular problem. Um, there's really no particular problem about that. But I'll go ahead and state it for complex numbers since that's what Rudin does. And we'll try to stick to that. So this is a set V. Elements Elements are called vectors. Okay. So V is supposed to be our vector space. Um, and an operation on vectors. If we have V and W, then we can add them together in a way that is associative. So, V plus W plus U equals V plus W plus U with the parentheses over here. Okay. Um, there is a zero vector um, uh, such that V plus zero equals V. Um, oh, I forgot commutative. So V plus W is equal to W plus V. Okay. We have a zero vector. Um, and we have opposites so that uh, v plus the opposite of v is equal to the zero vector. Okay. Um, so that part of this here basically means that that V is an abelian group. Misspelled that here. Okay. With the operation plus. So if you know any group theory, I'm just saying that V is an abelian group. Um, Incidentally, this can be parsed. So the abelian part, oh, I messed up. Let me do this right. So there we go. So the abelian part actually just corresponds to the commutative property, and the rest of this has to do with being a group. Okay, so if you just keep everything else, you get a group. If you add the commutative part, that's called an abelian group. And if you're wondering, why don't you call it a commutative group? Well, you know, Abel is a person. So this is named for an actual person who studied these types of groups. Okay, so we have our little abelian group V. And then we have a scalar multiplication. So alpha is in R or C. So this is where the real or complex issue comes in. So our scalar is allowed to be in R if we're in a real vector space, and it's allowed to be in C if we're in a complex vector space. And and then we have a V in V, and then to that we assign another vector. Okay, so there's a way to do scalar multiplication that satisfies, let's see, 1 times v equals v. So that's the number 1 that's in the real numbers and in the complex numbers. Um, uh, we have a kind of associativity, alpha beta v equals alpha beta v, if we parenthesize this way or this way. Okay, so we have a kind of associativity. Um, it's a little bit different from a normal associative property because V here comes from the vector space, whereas alpha and beta come from the field, which is given by the real numbers or the complex numbers here. Okay, and then we have distributive laws. So alpha times v plus w is equal to alpha v plus alpha w, standard distributive property, as well as alpha plus beta times v equals alpha v plus beta v. Okay, so that's distributive stuff. Okay. Of course, these two are different, right? Because the thing on the right is a vector, and the thing on the left is a scalar. But that's basically what we're dealing with a vector space. Um, and then we have a, linear transformation um, from a vector space. 2. And just because of the way this um yeah, no, well, okay. We'll do two vector spaces. So a linear transformation is a function between two vector spaces. Okay. Let it be abbreviated like this. Okay, such that um, if we do alpha v plus beta w inside the function, we can then do it outside the function. So basically, alpha is compatible with the addition and with the scalar multiplication. Okay. Now, um, if W is equal to R in the real case or C in the complex case. There's actually more to say here because technically C is a real vector space, so you you could do C in the real case also, but if W is equal to R or C, um, which are vector spaces via usual plus and times. So real numbers and complex numbers can be added and multiplied. And if you think through the axioms here of if you think through the axioms of a vector space, you should see that the set of real numbers as well as the set of complex numbers satisfy all these properties. Um, in the case of R, it's going to be a real vector space. In the case of C, it is both a real and a complex vector space. Basically because the complex numbers contain the real numbers. So it's not magic. But anyway, if this happens, then um, this what is it? Is this gamma? Hold on. Is this uppercase gamma? My Greek letter stuff. No, it's not gamma. What is it? Oh, it's lambda. Lambda. Right. Okay. Then lambda is called a linear functional. Okay. So now you know what a linear functional is. Okay. Um, and now I will observe that a few things. Um, so first of all, yeah, I think I'll go to a new page for this actually. So first of all, let's observe that if X is, I mean, it doesn't have to be really any kind of space in particular, but let's say locally compact Hausdorff space. So see previous video. So locally compact Hausdorff space. Um, Yeah, no, I didn't actually talk about what that was, but I at least talked about some properties of locally compact Hausdorff spaces. Um, I didn't want to actually do like heavy topological theory because yeah, I'm trying to get to the Riesz representation theorem here and if I did a full course in topology, it would take several videos to actually like build up the theory from scratch and get to the point where I can explain what a locally compact Hausdorff space is. It's nothing crazy if you've ever taken topology before. And I'm assuming that people watching this are people who at least have some basic familiarity with topology. And like I said before, if any of this interests you and you would like me to do a series of videos on topology, I'm very happy to do that. With anti-algorithm math, my general goal is to prove like interesting theorems in advanced math. Um, and some of those are going to be from topology for sure. Like I was thinking about doing what is it called? The product one. Oh no, it's been too long. What the product of compact is compact. Oh, I almost have it. Product of compact spaces is compact. What is that called again? Tikhonov, the Tikhonov theorem. God, I'm so out of practice. Yeah, Tikhonov theorem. I was thinking about showing you the proof of that. That involves axiom of choice, of course. The Tikhonov theorem is actually equivalent to the axiom of choice. Um, but I was thinking about proving that with the ultra filters because I think ultra filters are kind of fun and the proof is kind of intuitive once you get comfortable with the concept of ultra filters. That's something I got into a while ago. Obviously, you can look at Monkrez and see the proof there. Okay, sorry, I've digressed a bit. My point was that if you want to see some more ground level basic topology, just building up from the definition and talking about locally compact Hausdorff spaces and whatever's relevant here. I'm happy to do that. But I'm mainly doing what interests me unless I hear that there's interest for other things. So yeah, requests encouraged. So I leave that to you. You can put that in the comments, um, and I'll say more. Anyway, let's say we have a locally compact Hausdorff space. Then this continuous functions from X to C or R with compact support. Okay, uh, is uh, is a vector space over C or R. So it's a complex vector space or it's a real vector space, depending on whether your functions land in C or in R. Of course, the continuous functions to C are also a vector space over R, but um, anyway, I don't want to get into the finer points of that. That doesn't matter so much. My point is that the set of continuous functions with compact support out of a locally compact Hausdorff space is a vector space. Okay, and this could be any space. I mean, this could be a set actually. It doesn't need to have all this extra structure. We're going to use the fact that it's locally compact Hausdorff to construct certain continuous functions, and the Riesz representation theorem absolutely requires a locally compact Hausdorff space. You'll see how essentially that comes up in the proof. Um, but in terms of getting a vector space, it really doesn't matter. It doesn't matter if they have compact support. It doesn't matter if X is locally compact Hausdorff, right? As soon as you have functions that land in the field, right, either the complex numbers or the real numbers, you can add them, you can multiply them by a scalar, and all those laws hold, right? So if lambda from CCX to um, to C satisfies for f a real function and greater than or equal to 0. So when I say f is in R, I just mean that um, um, the output of f, yeah, let me be precise. Let me be precise. Because I don't really mean that f is in R. So for f, a continuous function with compact support, and the range is entirely contained within real numbers, and it's always positive. um, then lambda of f is real and lambda f is also positive. Okay, so if it satisfies this condition, okay, then we say that lambda is a positive linear functional. Okay. So that's going to be sort of essential in the statement of the Riesz representation theorem. Okay? So obviously this definition here also makes sense over R, right? And then this condition here is just vacuous, right? If it's already in R, then we don't have to worry about that. So this is what a positive linear functional is. It's fairly straightforward. It just means if you have a positive function, then the output, scalar of this linear functional is also a positive number, right? So a linear functional takes a function and outputs a real number or a complex number. Okay. And specifically in this case, if you start out with a real function that's always positive, then it has to output a positive number. That is the condition that we're going to need for a functional. And it's worth observe that um, um, mapping f to its Lebesgue integral is a linear functional. Um, uh, yeah, I don't want to get into the weeds. Uh, what I mean by that is it satisfies the linearity properties and it's positive as well. So actually, I should say a positive linear functional. Um, yeah, let me just do that real quick. Okay, yeah, positive linear functional on functions such that the integral is in C. Okay, all right. So you can prove to yourself that that's a vector space, and then you'll see this is a positive linear functional. And basically, this is the inspiration for the Riesz representation theorem. So this observes that uh, that you can view the Lebesgue integral as a positive linear functional. The Riesz representation theorem is going to tell you if you have a positive linear functional under various conditions, then you get a measure and a sigma algebra whose associated Lebesgue type integral represents the linear functional, right? That's basically the conclusion of this. Okay. So I think at this point, I'm ready to state the theorem. The theorem is a little bit long. Okay. Can I fit it on one page? Um, I guess we're gonna find out. Um, uh, actually, yeah, let me give one more example here. Um, so let's say F maps to the um, And we'll just do negative infinity to infinity however many times we need to. F of x dx, or it's like dx1, dx2, or whatever, right? Is a positive. So this is the Riemann integral. Is a positive linear functional on um, the continuous functions with compact support on Rn. Okay? So, you can check those properties. We know this is a vector space. Linearity properties are pretty straightforward. The fact that it's positive is pretty straightforward, right? If you have a real valued function and you do this Riemann integral, then you're going to get a positive number, right? That follows pretty easily from the definition of Riemann integral. So this is going to be the positive linear functional that we use as jumping off point to obtain a sort of extension of it um, as a Lebesgue type integral, right? So it's going to cover all of the cases that the Riemann integral does, but also provide us with some new measurable functions, which we can then integrate. Okay, so let's do the statement. Okay, finally, Riesz Representation Theorem. Okay, so X is locally compact Hausdorff. Lambda from CCX to C is a positive linear functional. Okay. Then there exists a sigma algebra um, M on X, which contains all Borel sets. So I talked about the Borel oops. I talked about the Borel sigma algebra in the previous video. I did not want to highlight that. I talked about the Borel sigma algebra in the previous video. So it's basically the sigma algebra generated by the open sets or by the closed sets. Um, and there exists a positive measure, unique actually. So let me add that. Just put that in red because that's a little bit of a separate issue. Positive measure mu on M, which represents lambda in the sense that A, lambda of f is equal to the integral over x of f d mu for all f in the continuous functions with compact support. Uh, and which has the following additional properties. Okay, so now we're gonna add on some properties here. So B, mu k is finite for every compact set K in X. All right. C for E in the sigma algebra M. We have the measure of E is equal to the infimum of the measures of V, where um, V is an open set that contains E. V open. Okay. So so this holds for all. Maybe I'll just add for all here. I've used that symbol before. Okay, so for all E in the sigma algebra, the measure can be obtained as the infimum of the measures of the open sets that contain it. Okay, that's a useful thing. D, um, if E is open or, and by the way, I mean the inclusive or here, or E is in M and um, has finite measure, then we can do the following. So the measure of E is equal to the supremum of the measures of the compact sets that are contained in E. All right. So we can approximate every set in the sigma algebra from above by open sets, the measure at least, and we can approximate the measure from below by compact sets, at least if E is open or if E has a finite measure. Okay? So if you think about these two, you might see the beginnings of how we might use the Eurozone lemma from part two, right? Because you see we're squeezed between compact sets and open sets, right? And we've got this functional, and so anyway, there's something there. Okay, and then finally part E, if E is in the sigma algebra, A is a subset of E, and E has measure 0, then A is also in the sigma algebra. Okay, so that basically just says that any subset of a set of measure 0 has to be in the sigma algebra as well. Okay? So that is the complete Riesz representation theorem for you. Okay, we have parts A through E here. Okay, obviously part A is the crucial one, and you'll see that the way the proof works, we prove some of this stuff along the way. Um, so B through D will sort of come when we're constructing and proving the sigma algebra and the measure part of things. Um, and then uh, let's see. Yeah, there's some notes in Rudin. You can read those if you want. So what Rudin does here is uh, what Rudin does here is prove uniqueness first. Okay, so the unique part of this is the first step that he takes here. So let's look at uniqueness of mu. So by C and D, mu is determined by its values on compact sets. Okay, So let me just explain that real quick. So here's C and D, right? So part C says that every set can be obtained as the infimum of the measures of open sets that contain that set, right? Open sets from above, right? So that means that if two measures agree on open sets, then they have to agree on the entire sigma algebra, right? If they agree on open sets, they agree on the entire sigma algebra. Okay, now if you look at part D, you see that if you have an open set, that the measure of that open set is determined by the measures of compact sets that are contained inside that open set. So if two measures have all the same values on compact sets, then two measures have all the same values on open sets, which means the two measures have all the same values on the entire sigma algebra, and therefore the measures are the same, right? So all we need to do is show that if we have two measures satisfying all of this, then they agree on compact sets, okay? So that's the initial plan here. Okay. So so we're going to prove, so now assume mu1 and mu2 satisfy the above. Okay. We will show that mu1 of k is equal to mu2 of k for k compact. And that will mean that they agree on the entire sigma algebra by the argument I just outlined. Okay, so fix k and epsilon. Okay, um, by uh, by B and C. Okay, let's just go back here. Ah, yes. So so by B, right? The measure of a compact set is finite. Okay, so by B, the measures of these compact sets are finite. Okay. By C, um, there exists. All right. And let me explain what I mean by there exists. Okay. So this is there exists. All right. Just handy shorthand for proofs. So by C, there exists a V containing K with mu2 of V less than mu2 of K plus epsilon. Okay, so let's just explain what I'm even talking about here. So the measure of K is the infimum, right, of these, right? Now, it's worth noting, by the way, that compact sets are closed. So compact sets are Borel sets. So compact sets are in the sigma algebra. Just in case you're worried about that, that's a background detail, but compact sets are in my sigma algebra. Anyway, the measure of K is equal to the infimum of the measures of open sets containing K. So we can get as close as we want to the measure of K, right? Which means positive measures are increasing, right? We can prove that with the countable additivity. I don't know if I did that last time, but it's pretty easy. You can look that up. So the measures of these are all greater than the measures of these, and the smallest of them, the greatest lower bound, I shouldn't say the smallest of them. I should say the greatest lower bound of all of these is the measure of k, right? So here my E is going to be given by k, okay? So we can get as close as we want, which means that if we are a little bit larger than the measure of k, so, uh, mu 2k plus epsilon is a little bit larger than the measure of k. So that means we should be able to find an open set that contains k that has a smaller measure than that. Okay, it's also larger than the measure of k, but that's not essential to our discussion, or that is not worth stating at this time, shall we say. Okay, now, continuing by Eurozone, there exists an F such that F is trapped between K and V. Okay, so we talked about that in part two. Okay, so I showed you how to derive the Rudin version of the Eurozone lemma from the standard version of the Eurozone lemma. I did not prove either one from scratch because that proof is rough. I mean, like I said, I take requests. I will do the proof of Eurozone lemma if you want. It's cool. I have no objection to it. But anyway. By Eurozone, there exists an F that is trapped between K and V. Okay, hence the mu1 K is equal to the integral over x of the characteristic function of K d mu. So I don't know if I talked about this. I feel like I should have, but if I didn't, this property holds for any Lebesgue type integral. The integral of the characteristic function gives you the measure of that set. Okay, so I talked about characteristic functions last time. I mean, this is just a function that is 1 on k and 0 everywhere else. So the resulting integral really should give me the measure. And I should say d mu 1 here to clarify we're doing the first one. Okay? And because this, right? Because f is equal to 1 on k, and the characteristic function here, this one, chi k, is it chi? Sorry, yeah, it's chi. Um, so chi k, uh, that sounds weird. Anyway, chi k is 0 outside of k, right? Whereas f is positive and it's equal to 1 on k. Therefore, um, f is greater than or equal to chi k, and so then we have this inequality here, okay? And then um, by the fact that we have the Riesz representation theorem, right? Uh, both of these measures and sigma algebras and so on um, well, we're assuming there's one sigma algebra but two positive measures, right? That's the idea. So we have two measures, and each of these measures integrals represent the given positive linear functional. So that's how we can kind of climb between the two, okay? Because we know this is also equal to f of d mu 2, right? So this just comes from part A, right? This just comes from this because we have mu 1 and a mu 2 that satisfy this, right? So that's going to help us relate them. Okay, now because the support of f is contained in V, right? All the values where f is not equal to 0, right, are contained in V. And the characteristic function of V, and f is also between 0 and 1, right? That's like part of what this definition means. So anyway, this part right here now tells me that this, okay, if you're following here, is less than or equal to um, the integral over x of chi v, so the characteristic function of V d mu 2. Okay, which again, just like the first equality here, the integral of a characteristic function is the measure of the set, right? So this is mu2 of v, okay, which is less than mu 2k plus epsilon by the assumption up here, right? Or by the way we chose v up here, right? We chose v to be close, right, to mu 2 of k. So so now I have that mu 1 of k is less than mu 2 of k um, plus epsilon. And if we let epsilon go to 0, we get that mu 1 of k is less than or equal to mu 2 of k. Okay, but by symmetry, okay, because the 1 and the 2 didn't matter here at all, mu 2 of k is less than or equal to mu 1 of k. And so they're equal on k, right? Which is what I wanted to prove. Okay, so that's the end. That's the end of that argument. Okay, so that shows that the measure is unique, right? So I'm not exactly stating that the sigma algebra is unique, though I think if you look at how the sigma algebra is constructed, you'll see that the sigma algebra is also um, it can only be one thing if it comes from the same linear functional. So if we start with the same linear functional and we feed it into the Riesz representation theorem, we're going to get the same sigma algebra and we're going to get the same measure. It's not just that there is one, it's that it's the only one that really does this, okay? Just existence is already cool. But what this tells you here is that if you have another one that does the job, then it must be the same. So this is going to be a way to see that, or a way to approach seeing that if you construct Lebesgue measure in a different way, right? And you see that it extends the Riemann integral on continuous functions with compact support, and you prove it has these other properties, then you will know that that Lebesgue measure has to agree with this Lebesgue measure. Okay? So, so having uniqueness is actually pretty cool here because it tells us that we're not just getting a Lebesgue measure, we're getting the standard one, right? Assuming that the standard one has these properties, right? Which it does, for the record. Um, you can look that up. It's going to have the properties by construction here, but if you construct a big measure using outer measure, for example, like many textbooks do, and I thought about doing a series where we do the outer measure approach so you can see how different it is and maybe unifying the two. I don't know. I don't want to do analysis for the rest of my life, so maybe it's something else. But anyway, um, this tells you that, however you approach it, as long as you stay within the boundaries of like some basic properties, you're going to all be doing the same measure and the same sigma algebra. So I think that's a cool thing to realize. Okay, so yeah, at this point, I don't think I have time. Um, at this point, I don't think I have time to dive into the proof of the Riesz representation theorem, so I guess I'm going to leave that. I'm not sure I can actually even do the whole proof in one video. I kind of think I can't. But what I want to close out with here is how to get Lebesgue measure from the Riesz representation theorem. So, like I said before, if we look at the Rn Riemann integral on CCX, or CCRN is what I mean here, is a Positive linear functional. Let's see, what did I need is a positive linear functional on Rn, which is locally compact Hausdorff. Um, I think that's all I need. Yeah, yeah. So if you know anything about the Riemann integral, and you'll forgive me for using Lebesgue type notation. The only reason I did that is I wanted to avoid writing a bunch of nested integrals with infinity signs, but I don't know. Maybe I should actually do that. Okay. So, we integrate from negative and we do like dx1, dx2, dxn. Okay. So that's the Riemann integral here. Um, yeah, let me repair this just a little bit. There we go. Just want to make this as legible as I can because this is kind of the big point I'm trying to make here. Okay. So, we integrate in each variable. You can think about if you have a continuous function with compact support, it's a continuous function with compact support, on each variable separately. So it's going to have a finite integral in each variable, and we just do them one at a time. And we can do them in any order, it doesn't matter. Going back to Fubini or whatever, Riemann version of Fubini, not the actual Fubini theorem, which is a thing from this book. Um, anyway, right, if f is a positive function, then the Riemann integral is going to be positive, right? And it has those linearity properties. So the associated sigma algebra and mu are um, the Lebesgue sigma algebra and measure respectively. And as a bonus, we get that this iterated integral from negative infinity to infinity f dx1 through dxn will be equal to the integral over Rn of f d mu. Okay? For f a continuous function with compact support on Rn. Oops. Go. R. Okay. So that's how we're gonna get Lebesgue measure out of this. I should mention amusingly that Uh, and I'll just put this in a comment here. Rudin does an ad hoc construction of this. Basically to like Rudin wants to be complete, right? I mean, he includes like stuff from scratch. Like he keeps it real limited in terms of the amount of background. Like looking through that first chapter, I mean, he does what a union is and what an intersection is, what an inverse image is, right? Basic set algebra. He defines every single thing that he uses. He's doing this whole thing from scratch. So he is not relying on theorems about the Riemann integral. He actually constructs it in this weird ad hoc way. I mean, to me, it's weird because like the standard way to do it feels a little bit friendlier to me, but he sort of comes up with a thing that has to give you the Riemann integral, and then uses that to get Lebesgue measure. I don't really want to talk about his ad hoc construction of the Riemann integral because the Riemann integral is very well known. Um, so you can check out the book if you want to see his ad hoc construction of the Riemann integral. I just wanted to show you that this is the big takeaway of the Riesz representation theorem. We build it as we build our new Lebesgue integral as an extension of our old Riemann integral. And to me, that's actually like just a beautiful thing. And that's why I wanted to go over this because I think it's cool. Um, Okay, so I mean, based on the time I've been taking, um, I think I'll stop here. And next time I will dive into the proof of the Riesz representation theorem. Now that you see what the value is, I don't say this is the only way that you could possibly use the Riesz representation theorem, but it's a very powerful usage because something I forgot to say in the first video is it's very easy to write down um, the axioms for a sigma algebra and for a positive measure and so on. It's very easy to write those down, but to come up with interesting examples is no joke, right? If you're doing group theory, right, abstract algebra, if you're doing topology, right, it actually isn't insanely hard to come up with very interesting examples without too much trouble, right? But in the case of these topics, coming up with interesting examples is kind of challenging. And you can see how much heavy machinery we are throwing at this. And even if you construct Lebesgue measure in the other way, it still involves a considerable amount of work. So there's just no way around it, right? This is a deeper topic than than those other bits of theory, right? And that's why, in Bourbaki or whatever, uh, analysis comes later, right? Because it is building on the foundation of all of this previous stuff. Okay, so with that, I will say thank you for watching, and I'll see you next time for the proof of the theorem. All right. Bye, everybody.